Hello, and welcome to Sleepy Engineering. In this video, we will explore one of the most fascinating and essential questions in the history of technology. How do planes work? This narration is intentionally slow, detailed, and repetitive. It is designed to help you relax, to help you focus, or to help you fall asleep. There will be no sudden sounds, no music, and no emotional tone. Only the steady voice of information. An airplane is a machine that defies gravity, staying in the air through a careful balance of forces and engineering design. From the wings that generate lift, to the engines that provide thrust, to the control surfaces that guide stability, every part of an airplane has a specific function that allows it to fly safely and efficiently. Over the course of this video, we will look step by step at the principles of flight, the structure of airplanes, and the systems that make them operate. The story will unfold slowly, without rushing, so you can take in each detail calmly. Now, please sit back, close your eyes if you like, and let the quiet journey into the world of flight begin. The question of how an airplane manages to rise from the ground and remain suspended in the air has fascinated people for centuries. And the explanation lies in the careful balance of forces that act on the aircraft at every moment of flight. In order to understand the principles of flight, we must consider the four fundamental forces that govern the movement of an airplane. These are lift, weight, thrust, and drag. Each force plays a distinct role, and the interaction between them determines whether an airplane will ascend, descend, or maintain level flight. Lift is the upward force that opposes the weight of the airplane. Weight is the force of gravity that pulls the airplane downward toward the earth. Thrust is the forward force produced by the engines, whether they are propellers or jet turbines, and it propels the airplane through the air. Drag is the resistance of the air against the forward motion of the airplane, which acts in the opposite direction of thrust. The principle of flight is achieved by managing these four forces so that they balance each other in such a way that the airplane can move steadily through the sky. The generation of lift is one of the most important aspects to consider. Wings are designed with a specific shape called an airfoil, which has a curved surface on top and a flatter surface on the bottom. As air flows over and under the wing, the shape of the airfoil causes the air pressure above the wing to be lower than the pressure beneath it. This pressure difference creates an upward force, which is lift. At the same time, the wing's angle relative to the oncoming air, known as the angle of attack, plays a major role in how much lift is produced. A greater angle of attack increases lift up to a point. But if the angle becomes too steep, the airflow over the wing can become disrupted, resulting in a stall where lift suddenly decreases. Weight, on the other hand, is constant as long as the mass of the airplane does not change significantly. It always acts downward due to gravity and must be overcome by lift for the airplane to rise. The engines of an airplane provide thrust, which allows the aircraft to move forward. In propeller-driven airplanes, the propellers spin and pull air backward, creating a forward reaction force that pushes the plane ahead. In jet engines, air is sucked in, compressed, mixed with fuel, and ignited, producing a high-speed exhaust that propels the airplane forward. Without thrust, there would be no movement through the air, and without movement, the wings would not generate lift. Drag resists thrust and is caused by the friction of air molecules as they flow around the surfaces of the airplane. Engineers design airplanes with streamlined shapes to reduce drag as much as possible, since overcoming drag requires more thrust, which in turn means more fuel consumption. The balance between thrust and drag determines whether the plane speeds up, slows down, or maintains a constant velocity. In steady level flight, lift equals weight and thrust equals drag. If lift becomes greater than weight, the airplane will climb. If lift is less than weight, it will descend. If thrust exceeds drag, the airplane will accelerate, and if thrust is less than drag, it will decelerate. This constant balancing act is the essence of flight. Another important principle is that air itself is a fluid, and the flow of air over the wing can be understood using principles of fluid dynamics. Bernoulli's principle, which states that an increase in the speed of a fluid occurs simultaneously with a decrease in pressure, helps explain why faster moving air over the curved upper surface of the wing produces lower pressure. At the same time, Newton's third law of motion, which says that for every action there is an equal and opposite reaction, also contributes to understanding lift. As the wing deflects air downward, the air pushes the wing upward in response. Both explanations work together to provide a complete picture of how lift is generated. Stability is another factor tied to the principles of flight. Airplanes are designed to maintain balance in pitch, roll, and yaw, which are the three axes of movement. The tail of the airplane, with its horizontal and vertical stabilizers, provides forces that counteract unwanted movements, ensuring that the airplane does not pitch nose up or nose down uncontrollably or veer off to the side. Control surfaces, such as ailerons, elevators, and rudders, allow pilots to intentionally manipulate the balance of forces to change direction and altitude. The atmosphere itself also plays a role in the principles of flight. Air density decreases with altitude, which means that at higher altitudes, there are fewer air molecules to create lift and to provide oxygen for combustion in engines. This is why airplanes require longer runways at high-altitude airports, and why jet engines are carefully engineered to perform efficiently even in thin air. Weather conditions, such as wind, turbulence, and temperature further influence flight, as they alter the distribution of forces acting on the airplane. The principles of flight are not just theoretical, but are applied practically in every aspect of aviation. Before takeoff, pilots calculate weight and balance to ensure the airplane is not overloaded and that the center of gravity is within safe limits. During flight, they adjust throttle settings to manage thrust, use control surfaces to direct airflow, and monitor instruments to maintain a balance between lift, weight, thrust, and drag. Engineers also apply these principles when designing new aircraft, ensuring that wings produce adequate lift, that engines deliver sufficient thrust, that the shape of the fuselage minimizes drag, and that the overall structure can withstand the forces acting on it. In summary, the introduction to the principles of flight reveals that flying is not magic, but the result of physics applied through careful engineering. Lift overcomes weight, thrust overcomes drag, and the interplay of these four forces allows an airplane to rise, to stay aloft, and to travel across the world. Understanding these principles provides the foundation for exploring all other aspects of aviation, from wing design and propulsion systems to control mechanisms and advanced aerodynamics. The structure of an airplane: wings, fuselage, and tail. To understand how airplanes function, it is necessary to study the structure that makes controlled flight possible. And at the core of every aircraft are three fundamental parts: the wings, the fuselage, and the tail. Each of these components has a specific role, and together they create a stable and functional machine that can generate lift, carry passengers or cargo, and maintain balance in the air. The wings are perhaps the most recognizable and essential part of an airplane, as they are responsible for generating lift. Their shape, known as an airfoil, is carefully designed so that air flows faster over the top surface than it does beneath the wing, creating a difference in pressure that produces an upward force. Wings come in many shapes and sizes, depending on the purpose of the airplane. Long, slender wings with high aspect ratios are common in gliders and commercial airliners because they reduce drag and provide efficient lift over long distances. Shorter, thicker wings are often found on fighter jets and aerobatic aircraft, where maneuverability and strength are more important than efficiency. The wings also house critical systems, including fuel tanks in many aircraft, as well as control surfaces such as ailerons and flaps. Ailerons are movable sections near the wingtips that allow the airplane to roll left or right by increasing lift on one wing and decreasing it on the other, while flaps are located closer to the fuselage and can be extended downward to increase lift during takeoff and landing. Some wings also contain spoilers, which can disrupt airflow to reduce lift and increase drag, helping the aircraft descend or slow down after landing. The structural integrity of the wing is another vital factor. Wings must be strong enough to support the entire weight of the airplane in flight and to withstand turbulence and stress. Engineers design wings with spars and ribs that distribute forces evenly, and materials such as aluminum alloys and advanced composites provide strength while minimizing weight. The fuselage is the central body of the airplane, and it serves as the main structural component to which the wings and tail are attached. Inside the fuselage is where passengers, crew, or cargo are housed, and it also contains the cockpit, where pilots control the airplane. The shape of the fuselage is typically streamlined to minimize drag, allowing the airplane to move smoothly through the air. For passenger aircraft, the fuselage must also meet strict safety requirements, with pressurized cabins to allow flight at high altitudes and reinforced structures to withstand changes in pressure. Cargo aircraft often have larger fuselages with wide openings for loading and unloading goods, while military aircraft may have narrower fuselages designed for speed and stealth. The fuselage also accommodates critical systems, including avionics, wiring, and hydraulic lines that connect various parts of the airplane. The structural design of the fuselage must ensure not only aerodynamic efficiency, but also safety and comfort for those on board. It must be strong enough to withstand the stresses of takeoff, flight, and landing, yet light enough to keep fuel consumption low. Advanced materials such as carbon fiber reinforced polymers are increasingly used in fuselage construction because of their excellent strength-to-weight ratio. The tail, also called the empennage, is located at the rear of the airplane and provides stability and control. It typically consists of a vertical stabilizer, a rudder, a horizontal stabilizer, and elevators. The vertical stabilizer is a fixed fin that prevents unwanted side-to-side motion, known as yaw. Attached to it is the rudder, which can be moved left or right to control yaw intentionally, allowing the pilot to steer the airplane's nose. The horizontal stabilizer prevents unwanted up and down motion, known as pitch. Attached to it are the elevators, which control pitch by moving up or down, raising or lowering the airplane's nose. In some modern aircraft, the horizontal stabilizer is designed as an all-moving surface known as a stabilator, which improves control at higher speeds. The tail also plays a crucial role in maintaining balance. Without it, an airplane would be unstable and uncontrollable, as the forces of lift and thrust would cause the aircraft to pitch, roll, or yaw unpredictably. Engineers carefully design the size and shape of the tail to ensure proper stability, taking into account the overall weight and aerodynamic properties of the airplane. Some aircraft, such as fighter jets, may have additional control surfaces or canards located near the nose that provide further stability and maneuverability. The integration of the wings, fuselage, and tail creates a complete structure that can withstand the stresses of flight while maintaining aerodynamic efficiency. The wings provide lift, the fuselage provides space and structure, and the tail provides stability and control. Each component is carefully engineered to complement the others, creating a harmonious balance that allows safe and efficient flight. As aircraft have evolved, the structure of these parts has adapted to meet new challenges. For example, early airplanes were built with wood and fabric, which were lightweight but not as durable as modern materials. As aviation technology advanced, aluminum became the standard material due to its strength, lightweight, and resistance to corrosion. In recent decades, composites have taken an increasingly important role, as they offer even greater efficiency by reducing weight without compromising strength. The design of the airplane structure also varies depending on the mission of the aircraft. A commercial airliner must prioritize passenger comfort, cargo capacity, and fuel efficiency, while a military jet must prioritize speed, agility, and strength. Cargo planes require wide fuselages and strong wings to support heavy loads, while gliders rely on long wingspans for maximum lift with minimal drag. Despite these variations, the fundamental structure of wings, fuselage, and tail remains consistent because it provides the optimal solution for controlled flight. In conclusion, the structure of an airplane is a masterpiece of engineering where every part has a purpose. The wings generate lift and house critical control surfaces. The fuselage carries people, cargo, and systems while maintaining aerodynamic shape, and the tail ensures stability and control. Together, these elements form a balanced and efficient machine capable of defying gravity and transporting people and goods across the world. Understanding the structure of an airplane is essential to appreciating the complexity and beauty of flight, and it provides the foundation for exploring more advanced aspects of aerodynamics and aviation technology. At the very heart of flight lies the concept of lift, the upward force that allows an airplane to rise off the ground and stay in the air, despite the constant pull of gravity. Understanding lift requires a careful examination of both the physical properties of air and the way wings are designed to manipulate that air. One of the most commonly cited explanations of lift is Bernoulli's principle, which states that as the speed of a fluid increases, its pressure decreases. Since air is a fluid, this principle can be applied to airflow over the surface of a wing. The shape of the wing, known as an airfoil, is curved on the top and flatter on the bottom. When air passes over the wing during flight, the curved upper surface forces the air to travel faster than the air moving beneath the wing. According to Bernoulli's principle, the faster moving air on top creates an area of lower pressure, while the slower moving air beneath the wing maintains higher pressure. This pressure difference produces an upward force on the wing, which we recognize as lift. However, Bernoulli's principle is only one part of the explanation. Another essential concept is Newton's third law of motion, which states that for every action there is an equal and opposite reaction. As the wing moves through the air, it deflects air downwards. The downward push of air is the action, and the equal and opposite reaction is an upward push on the wing, which adds to the total lift generated. This interaction between airflow and the wing surface helps clarify why lift occurs, not just because of pressure differences, but also because of the redirection of air. In addition to the shape of the wing, the angle of attack is a critical factor in determining how much lift is produced. The angle of attack is the angle between the wing's chord line, which is an imaginary line running from the leading edge to the trailing edge of the wing, and the direction of the oncoming air. At small angles of attack, lift is relatively low because the wing is not deflecting much air downward. As the angle of attack increases, the wing generates more lift because it redirects more air and intensifies the pressure differences between the top and bottom surfaces. However, there is a limit to this increase. If the angle of attack becomes too steep, the airflow over the top of the wing can no longer remain smooth and attached to the surface. This results in a turbulent wake behind the wing, known as flow separation, which causes a rapid loss of lift. This phenomenon is called a stall, and it is one of the most important considerations in the design and operation of aircraft. Pilots must be trained to recognize and recover from stalls, and engineers must design wings and control systems to minimize the risk of stalling during normal operations. The interaction between Bernoulli's principle, Newton's laws, and the angle of attack shows that lift is not the result of a single factor, but rather the combination of several aerodynamic effects. The velocity of air over the wing, the pressure differences it creates, the downward deflection of air, and the position of the wing relative to the airflow all contribute to the total lift force. This is why pilots and engineers must always think of flight as a balance of forces rather than a single mechanism. Another important detail in the physics of lift is that the amount of lift produced also depends on the speed of the airplane and the density of the air. At higher speeds, more air flows over the wing per unit of time, which increases lift. At higher altitudes, however, the air is less dense, which reduces the amount of lift generated at the same speed. This is why airplanes require longer runways to take off at high-altitude airports, and why wings are sometimes designed with larger surface areas to increase lift in thin air. Air temperature and humidity also influence air density and thus affect lift. In modern aviation, engineers design wings with specific shapes to optimize lift for the intended purpose of the aircraft. Long, narrow wings with high aspect ratios are efficient for producing lift with minimal drag, making them ideal for gliders and commercial airliners. Shorter, broader wings with lower aspect ratios produce more lift at lower speeds, which is useful for fighter jets and aircraft that must operate from short runways. Some aircraft employ variable geometry wings or flaps that extend to increase the surface area and angle of attack during takeoff and landing, enhancing lift when it is most needed. These adaptations reflect how the physics of lift is applied in practical engineering solutions. Lift is not only about keeping an airplane aloft, but also about maintaining stability and control. Engineers design wings with specific twists along their length, a feature known as washout, to ensure that stalls occur at the wing root first, preserving aileron control near the tips. This makes the airplane safer and easier to handle. Additionally, devices such as slats and vortex generators are used to improve airflow over the wing, delaying stall and increasing lift at higher angles of attack. These features demonstrate how deeply the principles of lift influence the detailed design of aircraft. In summary, the physics of lift combines several principles of fluid dynamics and mechanics. Bernoulli's principle explains how pressure differences arise due to variations in airflow speed. Newton's laws explain the upward reaction created by deflecting air downward, and the angle of attack determines how effectively these forces interact. Together, these factors create the lift that allows an airplane to fly. Without a clear understanding of lift, it would be impossible to design safe and efficient aircraft, and without the careful balance of these aerodynamic principles, controlled flight would not be possible. While lift allows an airplane to rise into the air, it would not be possible without thrust, the forward force that pushes the aircraft through the atmosphere and enables the wings to generate that necessary lift. Thrust is created by engines, and over the history of aviation, several propulsion systems have been developed, each with different strengths, applications, and levels of complexity. To understand thrust, one must begin with Newton's third law of motion, which states that for every action, there is an equal and opposite reaction. An engine generates thrust by accelerating air backward, and the equal and opposite reaction pushes the airplane forward. This basic principle applies whether the airplane uses a propeller or a jet engine. In the earliest days of powered flight, propellers were the dominant method of generating thrust, and they are still widely used today in small aircraft. A propeller is essentially a rotating wing designed as an airfoil which spins rapidly and pulls air backward. The motion of the blades lowers the pressure in front of the propeller and increases pressure behind it, producing thrust. The efficiency of a propeller depends on its design, the number of blades, and the speed of rotation. And while they are effective at low to moderate speeds, they become less efficient at very high speeds due to compressibility effects in the air. Jet engines were introduced in the 20th century and transformed aviation by enabling much higher speeds, greater altitudes, and longer ranges. The most common type of jet engine in commercial aviation is the turbofan. A turbofan engine works by drawing air into a large fan at the front, compressing it with multiple compressor stages, mixing it with fuel in a combustion chamber, and igniting the mixture. The hot gases expand rapidly and exit through a turbine and nozzle, producing thrust. The turbines extract some of the energy from the expanding gases to drive the compressor and the fan at the front, creating a continuous cycle. A portion of the air bypasses the combustion chamber and flows around the core of the engine, which increases efficiency and reduces noise. The ratio of bypass air to core air is called the bypass ratio, and modern turbofan engines with high bypass ratios are more fuel efficient and quieter than earlier designs. Other types of jet engines include turbojets, which were the first generation and are simpler in design, producing thrust entirely from the exhaust gases. Turbojets are efficient at very high speeds, but consume large amounts of fuel, making them less practical for commercial use today. Turboprops are a hybrid design, where a jet engine drives a propeller, combining the advantages of propeller efficiency at low speeds with the power of jet propulsion. Turboshaft engines are similar, but are designed to drive a shaft, commonly used in helicopters. In the field of military aviation, afterburning turbojets and turbofans are used to achieve supersonic speeds. An afterburner injects additional fuel into the exhaust stream behind the turbine, producing a dramatic increase in thrust, but at the cost of very high fuel consumption. These engines provide the performance necessary for fighter jets and interceptors, but are not practical for commercial aircraft. The design of an engine also involves careful consideration of aerodynamics, materials, and thermodynamics. The compressors must squeeze air to very high pressures without causing stalls or surges, and the turbine blades must withstand extreme temperatures while rotating at thousands of revolutions per minute. Engineers use advanced materials such as nickel-based superalloys and ceramic coatings to endure these conditions, and computer models optimize the shapes of blades and fans for maximum efficiency. Thrust is not only about raw power, but also about matching the engine to the mission of the aircraft. A small general aviation airplane may only require a lightweight piston engine driving a propeller, while a large commercial airliner requires multiple turbofan engines, each producing tens of thousands of pounds of thrust. Cargo planes, private jets, drones, and helicopters all use engines designed to meet their specific requirements of speed, altitude, range, and load capacity. Another key aspect of thrust is fuel efficiency. Aviation fuel is a major cost for airlines, and reducing consumption also reduces environmental impact. Modern turbofans achieve remarkable fuel efficiency through high bypass ratios, advanced aerodynamics, and digital engine control systems. Engineers are also exploring hybrid electric propulsion systems and alternative fuels such as biofuels and hydrogen, which could reduce emissions and dependence on fossil fuels. Electric propulsion is being researched for smaller aircraft, where battery weight and energy density are significant challenges, but improvements are being made. Propulsion also determines the ability of an airplane to perform takeoff, climb, cruise, and landing. During takeoff, engines must produce maximum thrust to accelerate the airplane along the runway until lift exceeds weight. During climb, sufficient thrust is required to overcome drag and gain altitude. At cruising altitude, engines typically operate at reduced thrust for efficiency, maintaining a balance where thrust equals drag. During descent, thrust may be reduced further or even set to idle, allowing drag and gravity to lower the aircraft, while at landing engines may provide reverse thrust by redirecting airflow to slow the airplane. In addition to powering the aircraft, engines also provide bleed air and electrical power to support onboard systems, such as air conditioning, pressurization, and avionics. The integration of engines with the rest of the airplane is thus critical not only for propulsion, but also for overall operation. In conclusion, thrust and propulsion are the driving forces that make flight possible, transforming chemical energy from fuel into mechanical motion through carefully engineered systems. From the spinning blades of a propeller to the roaring turbines of a modern jet engine, propulsion systems embody the application of physics, engineering, and innovation. The ability to design engines that provide reliable thrust while balancing efficiency, performance, and environmental impact is one of the greatest achievements of aviation technology. Without thrust, wings could not generate lift, and airplanes would remain grounded. With it, humanity has gained the ability to cross continents, oceans, and even explore the edges of space, making thrust and propulsion central to the story of how planes work. In order to fully understand how airplanes operate, it is important to examine the force that constantly works against them: drag. While lift allows the airplane to rise and thrust propels it forward, drag is the opposing force that resists forward motion through the air. Drag is created by the interaction between the surfaces of the airplane and the air around it. And managing drag is one of the central challenges in aviation engineering. There are several types of drag, each with distinct causes and effects, and pilots and engineers must always consider how to minimize or control them to achieve efficient flight. The first type is parasite drag, which includes form drag, skin friction, and interference drag. Form drag occurs because objects moving through the air must push molecules out of the way, creating resistance. The shape of the airplane determines how much form drag is generated, with streamlined shapes producing less drag than blunt or irregular ones. This is why aircraft fuselages, wings, and engine nacelles are carefully designed with smooth contours to allow air to flow cleanly around them. Skin friction drag arises from the fact that air molecules stick to the surface of the airplane, creating a thin boundary layer of slower moving air that increases resistance. Although this effect is small compared to form drag, it adds up significantly across the large surface area of a commercial airliner. Engineers reduce skin friction drag by polishing surfaces, using smooth materials, and applying coatings to minimize turbulence in the boundary layer. Interference drag occurs when airflow around different parts of the airplane meets and disrupts each other, such as at the junction of the wing and fuselage or around landing gear. Careful design of fairings and fillies helps reduce this type of drag by smoothing the airflow at intersections. Another important type is induced drag, which is directly linked to the production of lift. When a wing generates lift by creating pressure differences above and below its surface, the air beneath the wing tends to flow outward toward the wingtips, while the air above the wing flows inward. This creates swirling vortices at the wingtips, which represent energy lost in the form of induced drag. Induced drag is greater at low speeds and high angles of attack, which is why airplanes require longer runways to take off, and why they consume more energy when climbing. At higher speeds, induced drag decreases because the wings require a smaller angle of attack to generate the same amount of lift. Engineers use winglets, which are vertical extensions at the tips of wings, to reduce wingtip vortices and minimize induced drag. These winglets improve efficiency, save fuel, and are now a common feature on many modern aircraft. Wave drag becomes significant when airplanes approach the speed of sound. At transonic speeds, shock waves form on the wings and fuselage as the air is compressed and accelerated. These shock waves create a sudden increase in drag, which can make flight near the speed of sound inefficient and unstable. Supersonic and hypersonic aircraft are designed with special shapes, such as swept wings and pointed noses, to manage shock waves and reduce wave drag. While most commercial airliners cruise at speeds below the transonic region to avoid excessive wave drag, military jets and experimental aircraft must contend with it regularly. Engineers also consider additional sources of drag, such as cooling drag, caused by airflow required for engine cooling, and trim drag, which occurs when control surfaces are deflected to maintain balance. Even small components such as antennas, sensors, and landing gear doors can contribute to drag if not designed carefully. The importance of drag in aviation cannot be overstated, because drag directly influences fuel consumption, range, and performance. The more drag an airplane experiences, the more thrust is required to overcome it. And since thrust comes from fuel-burning engines, higher drag means higher fuel costs and greater environmental impact. Reducing drag has therefore been a priority for decades of aviation research. Streamlining has been one of the most effective strategies for minimizing drag. From the earliest days of flight, designers learned that smooth shapes resembling teardrops allowed air to flow with less resistance. Modern airplanes are the result of countless refinements in aerodynamic design, with every curve, angle, and surface carefully tested to reduce drag. Wind tunnel experiments and computer simulations help engineers predict airflow patterns and optimize designs. Materials science also plays a role, as smoother surfaces and advanced coatings further reduce drag. Pilots play a role in managing drag during flight. For example, extending flaps and landing gear increases drag dramatically, which is useful when slowing down for landing, but detrimental during cruising. Pilots retract flaps and gear quickly after takeoff to restore aerodynamic efficiency. Similarly, adjusting speed and altitude affects drag. Flying at optimal cruise speeds and altitudes ensures that drag is minimized relative to thrust, maximizing fuel efficiency. Some drag is actually beneficial, particularly when it helps control the airplane. For example, deploying spoilers on the wings increases drag intentionally to slow the aircraft during descent or after landing. In these cases, drag is not an unwanted force, but a tool used by pilots to manage energy and speed. Understanding the balance between beneficial and harmful drag is part of the art of flying. Future technologies continue to focus on reducing drag further. Concepts such as laminar flow wings, which maintain smooth airflow across a greater portion of the surface, promise significant efficiency improvements. Adaptive surfaces that change shape in response to airflow, inspired by bird wings, may also reduce drag by optimizing lift and resistance simultaneously. Alternative propulsion systems such as distributed electric propulsion, which uses multiple smaller engines spread across the wings, can reduce drag by integrating thrust with aerodynamic surfaces more effectively. In conclusion, drag is the force that resists flight. And while it can never be eliminated, it can be managed and minimized through careful design, materials, and operation. From the streamlined fuselage and polished surfaces of commercial jets to the winglets and adaptive controls of modern designs, every advancement in aviation has aimed to reduce the energy lost to drag. At the same time, drag is an inevitable companion of flight, reminding us that moving through the air always comes at a cost. Understanding drag is essential, not only for engineers designing aircraft, but also for pilots operating them, as the constant battle between thrust and drag defines the efficiency, performance, and safety of every journey through the sky. An airplane is not only required to generate lift and thrust to fly, it must also remain stable and controllable in the air to ensure that pilots can guide it safely to its destination. Stability refers to the natural tendency of an airplane to return to steady flight after being disturbed, while control refers to the pilot's ability to intentionally change the aircraft's orientation and trajectory. To achieve both stability and control, airplanes are equipped with specialized control surfaces, primarily ailerons, elevators, and rudders. These surfaces work by redirecting airflow, creating forces and moments that change the airplane's position along its three principal axes: roll, pitch, and yaw. The ailerons are hinged surfaces located near the trailing edge of each wing, usually close to the wingtips. They are responsible for controlling roll, which is the rotation of the airplane around its longitudinal axis, running from nose to tail. When a pilot moves the control stick or yoke to the left aileron moves upward, while the right aileron moves downward. The upward deflection reduces lift on the left wing, while the downward deflection increases lift on the right wing, causing the airplane to roll to the left. The opposite occurs when the control stick or yoke is moved to the right, rolling the airplane in that direction. This rolling action allows the airplane to turn, as banking the wings redirects part of the lift sideways, guiding the airplane along a curved path. Without ailerons, airplanes would not be able to perform coordinated turns effectively. Elevators are mounted on the horizontal stabilizer at the tail of the airplane and are used to control pitch, which is the rotation around the lateral axis running from wingtip to wingtip. When a pilot pulls back on the control stick or yoke, the elevators deflect upward, creating downward force on the tail. This force pushes the tail down and raises the nose of the airplane, increasing the angle of attack of the wings and thereby increasing lift, which makes the airplane climb. When the pilot pushes forward, the elevators deflect downward, raising the tail and lowering the nose, which decreases the angle of attack and reduces lift, causing the airplane to descend. Precise control of pitch is essential for maintaining altitude, performing takeoff and landing, and adjusting the aircraft's climb or descent rate. The rudder is attached to the vertical stabilizer on the tail and controls yaw, which is the rotation of the airplane around its vertical axis, running from top to bottom. When a pilot presses the left rudder pedal, the rudder deflects to the left, generating a force that pushes the tail to the right and turns the nose to the left. Pressing the right pedal has the opposite effect. While rudders can be used to turn the airplane, they are primarily employed to coordinate turns and counteract undesirable yaw, such as the adverse yaw produced when ailerons are used. Adverse yaw occurs because the downward deflected aileron increases both lift and drag, pulling the wing back slightly, while the upward deflected aileron reduces drag on the opposite wing. This imbalance tends to yaw the nose opposite to the direction of the roll. The rudder corrects this by adding yaw in the desired direction, ensuring smooth and coordinated turns. These three control surfaces together give pilots full authority over the airplane's orientation in three-dimensional space. Roll, pitch, and yaw are fundamental to maneuvering, and without precise control in all three axes, flight would not be safe or practical. Beyond the primary controls, secondary devices such as flaps, slats, spoilers, and trim tabs further refine stability and control. Flaps extend downward from the trailing edge of the wing near the fuselage to increase lift and drag, which is particularly useful during takeoff and landing. Slats, found on the leading edge of the wing, help delay stall by allowing smoother airflow at higher angles of attack. Spoilers extend upward from the wing surface to disrupt airflow, reducing lift and increasing drag, which helps slow the airplane and control descent. Trim tabs are small adjustable surfaces on ailerons, elevators, or rudders that allow pilots to fine-tune control inputs, reducing the need for constant pressure on the controls and making long flights more manageable. Stability itself is achieved through careful design of the airplane's structure. The horizontal stabilizer provides a counterbalancing force to ensure that the airplane does not pitch uncontrollably, nose up or nose down. The vertical stabilizer prevents unwanted yawing motions, keeping the airplane's nose aligned with its direction of travel. The dihedral angle of the wings, which means they are tilted slightly upward from root to tip, provides lateral stability by naturally correcting rolling disturbances. If a gust of wind tips one wing downward, the lower wing experiences increased lift due to its steeper angle to the airflow, rolling the airplane back toward level flight. This passive stability reduces pilot workload and contributes to safety. However, too much stability can make an airplane sluggish and difficult to maneuver, so designers must strike a balance between stability and responsiveness. Fighter jets, for example, are often designed with less inherent stability to make them more agile, relying on computer systems to assist pilots with constant adjustments. Airliners, on the other hand, prioritize strong stability to ensure passenger comfort and efficient long-distance travel. The ability to control an airplane depends not only on the design of the control surfaces, but also on the systems that transmit pilot inputs. In traditional airplanes, cables and pulleys directly connect the cockpit controls to the surfaces, while modern aircraft often use hydraulic systems or fly-by-wire technology. Fly-by-wire replaces mechanical linkages with electronic signals, allowing computers to interpret pilot inputs and apply them more precisely, while also providing automatic stability adjustments. This technology increases safety and efficiency, ensuring that the airplane responds smoothly even in turbulent conditions. In conclusion, stability and control are achieved through the combined action of ailerons, elevators, and rudders, supported by secondary devices and careful aerodynamic design. These surfaces allow pilots to guide the airplane in roll, pitch, and yaw, maintaining balance, executing turns, climbing and descending, and landing safely. The interaction between stability, which keeps the airplane steady, and control, which allows intentional maneuvering, is what makes practical flight possible. Without this balance, airplanes could not operate predictably or safely. Understanding the role of ailerons, elevators, and rudders reveals not only how airplanes are controlled, but also how human ingenuity has transformed the simple forces of air into reliable and precise machines, capable of carrying people and cargo across the globe. At the center of every airplane sits the cockpit, a space that serves as both the command center and the interface between human decision-making and mechanical response. The cockpit is where pilots control the airplane, monitor its systems, and make continuous adjustments to ensure safe and efficient flight. The instruments and controls inside the cockpit are carefully arranged to give pilots maximum awareness and authority over the aircraft, and they translate human input into mechanical actions that move the airplane's control surfaces, adjust engine power, and regulate essential systems. The most recognizable control in the cockpit of many airplanes is the control yoke or stick. Moving the yoke forward and backward changes the position of the elevators on the tail, controlling pitch. Pulling back on the yoke raises the nose, increasing the angle of attack and causing the airplane to climb, while pushing forward lowers the nose and reduces lift, causing descent. Turning the yoke left or right operates the ailerons, creating roll and allowing the airplane to bank into turns. In some airplanes, particularly fighter jets and modern commercial aircraft, a side stick is used instead of a central yoke. The side stick functions in the same way, but allows for more ergonomic design and improved visibility in the cockpit. The rudder pedals located on the floor are equally important. By pressing the left or right pedal, the pilot moves the rudder on the vertical stabilizer, controlling yaw. Rudder pedals are also linked to the nose wheel on many airplanes, allowing pilots to steer the aircraft while taxiing on the ground. Coordination between the yoke or stick and the rudder pedals is essential for smooth turns, as the rudder counteracts adverse yaw caused by aileron inputs. Alongside these primary controls, there are power levers known as throttles. By pushing the throttle forward, the pilot increases the amount of fuel delivered to the engines, generating more thrust. Pulling it back reduces thrust. In multi-engine airplanes, each engine has its own throttle, and pilots can adjust them individually for balance or in case of engine failure. In turbofan engines, additional controls for reverse thrust are available to help slow the airplane after landing. Together, the primary flight controls and throttles give pilots direct control over the main forces of flight. But the cockpit contains far more than just these systems. Instrument panels provide critical information about altitude, airspeed, attitude, heading, engine performance, and navigation. The attitude indicator, for example, shows whether the airplane is level, climbing, or banking, giving pilots spatial orientation even when visual references outside the cockpit are poor. The altimeter displays altitude by measuring air pressure, while the airspeed indicator shows the speed relative to the surrounding air. The heading indicator works with a magnetic compass to give direction, and the vertical speed indicator shows the rate of climb or descent. In modern cockpits, these instruments are often integrated into digital displays known as glass cockpits, which replace many separate dials with multifunction screens. These displays can be customized to show different types of information, reducing clutter and improving situational awareness. Flight management systems, autopilot, and navigation computers further assist pilots by automating routine tasks, calculating optimal routes, and maintaining stable flight when engaged. Yet even with automation, the pilot remains responsible for monitoring systems and intervening whenever necessary. The translation of cockpit inputs into movements of control surfaces can occur through mechanical, hydraulic, or electronic systems. In smaller airplanes, cables and pulleys connect the yoke, stick, and pedals directly to the control surfaces. While this system is simple and reliable, it requires more physical effort from the pilot and can be less precise in large or high-speed aircraft. Hydraulic systems amplify pilot inputs with pressurized fluid, reducing the physical effort required to move large surfaces, such as elevators and ailerons on heavy aircraft. Fly-by-wire systems, now common in modern airliners and military jets, replace physical linkages with electronic signals. When the pilot moves the side stick, sensors detect the input and send it to computers, which then command hydraulic actuators to move the control surfaces. Fly-by-wire allows for greater precision, lighter aircraft structures, and enhanced safety features, as the computers can filter inputs to prevent dangerous maneuvers that might overstress the airplane. Trim controls are another important element in the cockpit. These allow pilots to relieve control pressures by making small adjustments to the neutral position of the control surfaces. For example, when climbing, the pilot can set elevator trim so the airplane maintains its pitch angle without constant pressure on the yoke. Similarly, rudder and aileron trim can correct imbalances caused by crosswinds or uneven engine thrust. Proper use of trim reduces pilot workload and makes long flights smoother. Secondary controls, such as flaps, slats, and spoilers, are operated from the cockpit as well. Levers or switches allow the pilot to extend flaps on the wings to increase lift during takeoff or landing. Slats on the leading edge can be deployed to delay stall at high angles of attack. Spoilers are raised to disrupt airflow and reduce lift, aiding in descent and braking after touchdown. Pilots must carefully manage these devices, as improper use can disrupt the delicate balance of forces acting on the airplane. The cockpit also contains systems for communication and navigation. Radios enable pilots to talk with air traffic controllers, ground crews, and other aircraft, while transponders provide identification and position to radar systems. Navigation equipment, such as GPS receivers, inertial reference systems, and flight computers, guide the airplane along its route, ensuring accuracy over long distances and in poor weather conditions. The cockpit is designed with ergonomics in mind, placing critical controls within easy reach and arranging displays so that information can be absorbed quickly. In emergencies, this design allows pilots to act rapidly and confidently. Standardized layouts and procedures across different airplanes also ensure that pilots trained on one type can adapt more easily to another. In conclusion, the cockpit is where human intention becomes mechanical action, where a simple movement of the hand or foot is transformed into changes in pitch, roll, yaw, thrust, or aerodynamic configuration. The combination of primary controls, secondary devices, and advanced avionics makes it possible for pilots to guide airplanes safely across the skies. While technology continues to advance with increasing automation and computer assistance, the cockpit remains the essential interface between people and machines, a place where knowledge, skill, and engineering converge to create the miracle of flight. Among all the stages of flight, takeoff and landing are the most demanding and critical, requiring precise coordination of aerodynamics, engine power, pilot skill, and air traffic control. While cruising at altitude allows for relative stability and safety margins, takeoff and landing occur close to the ground, where there is little room for error, making these phases the focus of much training, engineering, and operational procedures. Takeoff begins with taxiing the airplane from the gate or parking area to the runway, guided by ground control. Once cleared for departure, the airplane aligns with the centerline of the runway, and the pilot advances the throttles to bring the engines to takeoff power. As thrust increases, the airplane accelerates rapidly down the runway, with airspeed indicators rising steadily. During this acceleration, pilots monitor critical speeds known as V-speeds. V1 is the decision speed, the point beyond which takeoff must continue even if an engine fails, because there is insufficient runway left to stop safely. VR is the rotation speed, the speed at which the pilot pulls back on the control column to raise the nose. V2 is the takeoff safety speed, ensuring that the airplane can climb even with one engine inoperative. These speeds vary depending on weight, runway length, weather, and aircraft type, and they are calculated carefully before each flight. As the pilot rotates the airplane at VR, the angle of attack increases, and the wings generate enough lift to raise the airplane into the air. The landing gear remains extended until a positive rate of climb is confirmed, at which point the gear is retracted to reduce drag. Flaps, which were extended to provide extra lift at low speeds, are gradually retracted as the airplane accelerates. The climb phase begins, transitioning from the runway environment to en route flight. Takeoff requires careful control of pitch to avoid stalling by rotating too steeply, as well as close monitoring of engine performance. Crosswinds must also be managed, with rudder inputs ensuring the airplane maintains alignment with the runway during the ground roll and initial climb. Engine failure procedures are rehearsed by pilots repeatedly in simulators, because the loss of thrust during takeoff is one of the most critical emergencies. Landing, in contrast, involves bringing the airplane from high speed and altitude back to the ground in a controlled and precise manner. The approach begins many miles from the runway, guided by air traffic controllers and navigation aids. Pilots reduce thrust and descend along a planned glide path, using instruments such as the instrument landing system to align with the runway in poor visibility. As the airplane descends, flaps are extended in stages to increase lift at lower speeds and maintain control while slowing down. The landing gear is deployed, creating drag, but providing the means to touch down safely. Speed is managed carefully, with reference to VREF, the landing reference speed, calculated based on aircraft weight and configuration. Too much speed results in a longer landing distance, while too little risks stalling. On final approach, the airplane must be precisely aligned with the runway centerline, and the descent rate must be controlled. Pilots adjust pitch and power continuously to stay on the glide slope. Crosswind landings require special techniques such as crabbing, where the airplane is flown slightly angled into the wind, or slipping, where rudder and aileron inputs counteract drift. As the airplane crosses the runway threshold, it enters the flare, a maneuver where the pilot gradually raises the nose to reduce the descent rate and achieve a smooth touchdown. The main landing gear contacts the runway first, followed by the nose gear. Upon touchdown, spoilers deploy to disrupt lift, shifting weight onto the wheels for braking. Reverse thrust may be activated by jet engines, redirecting exhaust forward to help slow the airplane, while wheel brakes are applied progressively. Auto brake systems can automate this process, ensuring consistent deceleration. Landing distance must be carefully managed, especially on shorter runways, wet surfaces, or high-altitude airports where braking effectiveness is reduced. Both takeoff and landing are influenced heavily by weather conditions. Strong crosswinds, low visibility, rain, snow, or icy runways increase risk and demand greater skill from pilots. Aircraft performance charts account for temperature, pressure altitude, and runway conditions to determine required runway length and safe speeds. Air traffic controllers play a critical role in sequencing takeoffs and landings to maintain safe separation between aircraft, ensuring efficient flow of traffic, even at busy airports. Engineering plays an equally important role in making takeoff and landing safe. Runways are designed with length, lighting, and surface markings to guide pilots. Aircraft are equipped with systems such as ground proximity warning, wind shear detection, and automatic landing capabilities to reduce risks. Modern autopilot and auto-land systems allow airplanes to land with minimal visibility, guided entirely by instruments, although pilots remain vigilant and ready to take over. Training and procedures are designed to prepare pilots for the complexities of takeoff and landing. Flight simulators replicate realistic scenarios, including engine failures at V1, rejected takeoffs, crosswind landings, and emergencies such as hydraulic or brake failures. This training ensures that pilots react correctly under pressure. In real flight operations, checklists are used systematically to confirm that every step, from configuring flaps and trim for takeoff to arming spoilers for landing, is completed properly. The critical nature of these phases is reflected in accident statistics, which show that most aviation accidents occur during takeoff and landing rather than cruising. This is not because these phases are inherently unsafe, but because they involve transitions, higher workload, and proximity to the ground. The industry has responded by focusing safety measures, design improvements, and training efforts on these stages of flight. In conclusion, takeoff and landing are the most complex and demanding parts of flying an airplane. They require the precise coordination of aerodynamic principles, engine power, pilot skill, and technological systems. From the careful calculation of V speeds during takeoff to the delicate flare just before touchdown, every detail must be executed with accuracy. Engineering design, pilot training, and procedural discipline all converge to make these phases safe and reliable. While cruising may seem to embody the freedom of flight, it is takeoff and landing that showcase the mastery of aviation, transforming the potential of flight into the reality of departing from one place and arriving safely at another. Airplanes are among the safest forms of transportation in the world, and this remarkable safety record is the result of rigorous engineering, redundant systems, and a deep understanding of aerodynamics. Modern aviation relies on a combination of mechanical reliability, computerized monitoring, pilot training, and aerodynamic design to prevent accidents and respond effectively to unexpected situations. Safety systems are built into every aspect of an airplane, ensuring that if one component fails, others can take over to maintain control and protect passengers and crew. At the heart of modern aircraft safety is redundancy. Critical systems such as hydraulics, electrical power, and flight controls are duplicated or even triplicated so that if one fails, backups immediately engage. For example, an airliner may have 3 independent hydraulic systems powering control surfaces, ensuring that no single failure renders the airplane uncontrollable. Electrical systems are similarly backed up with auxiliary generators, batteries, and in some cases ram air turbines that deploy into the airflow to generate emergency power. This redundancy allows airplanes to remain safe even in the event of multiple failures. Aerodynamic safety is also built into the very shape and structure of the airplane. Wings are designed with features that delay stall, such as carefully shaped airfoils and leading-edge slats that smooth airflow at high angles of attack. Winglets reduce drag and turbulence, improving stability as well as efficiency. The tail surfaces ensure stability in pitch and yaw, keeping the airplane aligned and level. Modern flight control systems enhance aerodynamic safety further by preventing pilots from unintentionally exceeding safe limits. Fly-by-wire systems use computers to interpret pilot inputs and apply only those commands that remain within the aircraft's structural and aerodynamic envelope. This means that if a pilot tries to pitch the airplane too steeply or roll too aggressively, the computer will moderate the command to prevent a stall or overstress. This protective function allows pilots to focus on flying without fear of pushing the airplane beyond safe performance. Avionics systems play a critical role in modern aviation safety. Cockpits are equipped with terrain awareness and warning systems that alert pilots to potential collisions with the ground, a technology that has dramatically reduced controlled flight into terrain accidents. Traffic collision avoidance systems monitor the skies for other aircraft and provide visual and auditory warnings, even issuing automatic instructions to climb or descend to maintain separation. Weather radar and storm detection systems allow pilots to avoid dangerous thunderstorms and turbulence, while advanced navigation systems keep airplanes precisely on course, even in poor visibility. Structural safety is also vital. Airplanes are built to withstand forces far greater than those encountered in normal flight, with margins that ensure survivability in extreme conditions. Materials such as aluminum alloys, titanium, and composite fibers are chosen for their strength, fatigue resistance, and ability to endure repeated stress cycles. Engineers design airplanes with fail-safe principles, meaning that even if a structural component cracks or breaks, loads are redistributed so that the aircraft remains controllable long enough for a safe landing. Regular inspections, maintenance schedules, and non-destructive testing ensure that even small flaws are detected before they pose a risk. Fire safety is addressed with built-in extinguishing systems for engines, cargo holds, and auxiliary power units. Smoke detectors monitor enclosed spaces, and pilots have immediate access to fire suppression equipment. Fuel tanks are designed with inerting systems that reduce the risk of explosion, using nitrogen-enriched air to displace oxygen in empty spaces. Cabin safety systems focus on passenger survival in emergencies. Pressurization systems maintain breathable air at high altitudes, and oxygen masks deploy automatically if cabin pressure is lost. Emergency lighting guides passengers to exits, and evacuation slides allow rapid egress. Seats and restraints are engineered to withstand impact forces, and floor-level lighting ensures visibility in smoke-filled cabins. Safety is also embedded in the operation of airplanes through rigorous pilot training and standardized procedures. Pilots practice emergency scenarios repeatedly in simulators, from engine failures to hydraulic losses to fire on board. Crew resource management emphasizes communication and teamwork, ensuring that all crew members contribute to problem-solving under stress. Checklists provide structured responses to both routine and emergency situations, ensuring that no step is overlooked, even in chaotic circumstances. Aerodynamics itself is a source of safety when properly understood and applied. Engineers design airplanes to have stable handling characteristics, making them easier to fly and less prone to dangerous oscillations. Automatic systems such as yaw dampers prevent Dutch roll, a type of instability that can occur at high speeds. Stall warning and protection systems alert pilots before dangerous conditions arise, and can even apply corrective inputs automatically. The balance of lift, weight, thrust, and drag is constantly monitored to keep the airplane within safe limits. Modern aviation also benefits from data monitoring and predictive maintenance. Flight data recorders track system performance in real time, and airlines analyze this information to detect patterns of wear or stress before they become failures. Sensors monitor everything from engine temperatures to hydraulic pressures, and maintenance crews replace or service components based on condition rather than waiting for them to fail. This predictive approach improves reliability and safety while reducing costs. Air traffic control contributes to safety by maintaining separation between airplanes, guiding them through congested airspace, and providing real-time weather and traffic updates. International regulations and standards set by organizations such as the International Civil Aviation Organization ensure that safety procedures are consistent worldwide. The collaboration between pilots, engineers, regulators, and air traffic controllers creates a layered system where multiple safeguards overlap, reducing the likelihood of accidents. In conclusion, safety systems and aerodynamic design form the backbone of modern aviation's reliability. Through redundancy, structural strength, computerized protections, pilot training, and careful aerodynamic design, airplanes achieve levels of safety unmatched by most forms of transportation. While the forces of nature cannot be eliminated, They can be managed and controlled with engineering ingenuity and operational discipline. Modern airliners are not just machines of efficiency, but also machines of safety, carrying millions of people across the skies with remarkable consistency. The seamless integration of human skill and advanced technology ensures that each flight is conducted within a carefully managed envelope of safety, making aviation one of the most secure achievements of modern engineering. As we reach the conclusion of this exploration into how airplanes work, it is clear that flight is one of the most remarkable achievements of human ingenuity. The ability to lift a machine that weighs many tons into the sky and guide it across vast distances is the result of centuries of experimentation, observation, and engineering refinement. The basic principles of lift, thrust, drag, and weight remain unchanged, but the ways in which engineers and scientists apply these principles continue to evolve. Looking toward the future, aviation stands on the threshold of another transformation, one shaped by environmental concerns, technological advancements, and the growing demand for global connectivity. One of the most pressing challenges in modern aviation is sustainability. Airplanes consume large amounts of fuel and contribute significantly to global carbon emissions. Engineers are developing new propulsion technologies to address this issue, including electric and hybrid electric systems that could power smaller aircraft with little or no emissions. Advances in battery technology may one day allow larger airplanes to fly entirely on electric power, though the energy density required remains a major challenge. Hydrogen is another promising alternative, with the potential to serve as a clean fuel if produced sustainably. Several manufacturers are already testing hydrogen-powered concepts that may reshape aviation within decades. Aerodynamics will also continue to advance, with new wing shapes, blended wing body designs, and adaptive surfaces that minimize drag and optimize performance across different phases of flight. These innovations could reduce fuel consumption and make airplanes quieter and more efficient. Materials science will contribute by introducing lighter and stronger composites, reducing weight and improving durability. Just as aluminum once replaced wood and fabric in early airplanes, the next generation of materials may bring further leaps in efficiency and safety. Automation and digital technology are also transforming the future of flight. Fly-by-wire systems have already revolutionized how pilots control airplanes, but the integration of artificial intelligence and advanced autopilot systems may further reduce pilot workload and enhance safety. Some research is exploring the possibility of single pilot or even fully autonomous commercial flights, though regulatory and psychological barriers remain. Air traffic management is evolving as well, with satellite-based systems improving global navigation and allowing more efficient routing. These systems will help reduce delays, save fuel, and increase capacity in crowded skies. Safety will remain central to all developments, with new technologies designed to reduce risks and respond faster to emergencies. Predictive maintenance, enabled by sensors and data analytics, already allows airlines to detect potential issues before they occur. Future aircraft may self-diagnose problems in real time, scheduling repairs and minimizing downtime. Enhanced flight simulators and virtual reality training will prepare pilots for complex scenarios with greater realism than ever before. The passenger experience will also evolve. Cabins may become more comfortable, quieter, and designed with health in mind, reducing the stress of long-haul travel. Connectivity will allow travelers to stay in touch and work seamlessly while in flight. The future may even include supersonic or hypersonic travel, reducing intercontinental journeys to just a few hours. Companies are working on designs that overcome the challenges of noise, fuel consumption, and shockwave drag that limited supersonic aircraft in the past. If successful, these airplanes could reshape the way people think about distance and time. However, the expansion of aviation must balance efficiency, speed, and environmental responsibility. Public pressure and international regulations are pushing the industry to innovate not just for performance, but also for sustainability. This means that future airplanes will likely combine multiple advancements, such as alternative fuels, advanced aerodynamics, and digital systems, to meet global goals for reducing emissions. While technology continues to evolve, the fundamentals of flight will always remain. Airplanes must still generate lift through their wings, create thrust through propulsion, counteract drag, and maintain stability and control. What changes are the tools and methods used to achieve these goals? In many ways, the future of aviation is a continuation of the same spirit of experimentation that guided the Wright brothers more than a century ago. Each generation of engineers builds on the knowledge of the past while seeking solutions to the problems of its time. In conclusion, the story of how airplanes work is not just a description of forces and mechanisms, but also a reflection of human progress. From wood and cloth biplanes to supersonic jets and future electric airliners, the evolution of flight demonstrates our ability to understand, adapt, and innovate. The airplane is more than a machine. It is a symbol of exploration, connection, and ambition. As we look to the future, airplanes will continue to carry people and ideas across the globe, shaping economies, cultures, and possibilities. The balance of safety, performance, and sustainability will guide their design, ensuring that aviation remains both a practical and an inspiring achievement. The skies of tomorrow will be filled with aircraft that embody the best of human creativity, reminding us that the dream of flight, once thought impossible, continues to soar higher with every new generation.